Hello, good morning.
I, sus- I suspect our European compatriots um, are unaware that the hour is off.
That's right.
So that's okay. Maybe they can use a little extra rest. I can go through this morning the work that I did over the weekend to prepare for the talk. Okay. So I'll just do a few of these. Here we go. All right. So now we can scroll down to the end. All right, so what I've done is I've implemented, I'm in the process of implementing all the translation paths. So right now we have a ROCOM evaluator, and I just finished on Saturday morning the implementation of from Pi, asynchronous Pi, into Yoshida combinators. And when I can find a few spare minutes, I'll do the implementation of the translation paths from the Yoshida combinators to the row combinators and the direct translation from Pi to the row combinators. So if you look here, I'll just show you how the code lines up with the math. So easiest things first, 0 goes to 0. The translation of a par is the par of the translations. The translation of a new or a replication is the replication of the translation. The translation of a new is the new of the translation. And the translation of output B on A is the combinator message B on A. And then the tricky one is the for comprehension. And the reason that is straightforward. What the Yoshida combinators do is they get rid of the binding, right? So they're getting rid of this bound variable here. So it's essentially a more subtle variant of the SKI translations. That's really what's going on. So let's check that these things are matched up over here, and then we'll look at the translation of the 4 is this funny 4-star translation of the translation of the continuation. And you can see that the 4-star translation is a little bit more sophisticated. So if we go here, we should see that the translation of 0 is 0. So if we have a pi 0, we should get a y 0. And that's exactly what happens. If we have a pi output, we should get a message combinator. That's what happens. If we have a pi replication, then we should get a, there's a little bit of a type chicanery that has to happen with Scala. And that's because these things are typed more generally than than straight up process expressions. But if it is a process expression, then we get a replication, a star expression of the translation of the continuation. And then the same is going to be true of everything else. So there's the names that we have in the new scope, and there's the internal process. So if we translate that, and that is in fact a Yoshida process expression, then we get a Yoshida new expression with the translated internal process and the new scope. And similarly, here's a pi par expression, so it has a left and a right. We translate these two, the left and the right, and as long as they're Yoshida process expressions, then we make a Yoshida par of those two. So this code is exactly these equations. Does that make sense?
Yes.
Cool. So then the only one that's even vaguely interesting is this one. So if we look here, if we have a pi input expression, so we have for comprehension, then there's the subject, that would be A. There's the object, that would be X. And we have the continuation, that's P. So we translate P, so that's this bit, translate P. And then we translate the pi 4 with the subject, the object, and the translation. So again, this equation is exactly this code. Correct by construction is the idea. So then we can just look at a few cases of these. We don't have to look at all the cases because Yoshida does a trick in her equation. So first of all, the equations are ordered. You need to run them in this order. But there's a lot of compression going on. In particular, C is not any, this C here is not any specific combinator. It's any combinator that has this signature, which means you can have as many things to the right of this position, but this position has to be positive. So if you look up here, we say what the polarities are. So there's only two things that could be. Actually, there's only one thing that could be, and that's a message. All the others are negative in the first position, right? So duplicator is negative in the first position. Forward, sequence, both branches are negative in the first position. So that one only applies to message. So basically, it's messages where you have no binding on the input or the output. That's what this side condition is. No binding for messages. This one, however, is even more complicated because there are lots and lots of things that have negative in the first position. Right. So in particular, everything else is negative in the first position. Right. So all of these things get covered by this rule. And so you apply this rule before you apply any of these specific rules here. Basically,
can I ask?
Yeah.
This W corresponds to all the other arguments.
All the other arguments. Yeah, exactly. That's right.
And can we use W on the right hand side because we don't have exact number or what are the types?
The only thing we're using is just putting the rest of the stuff in.
Okay.
We're just splicing them in. Yeah, that's all.
Okay. Okay, thanks.
Sure. So in this case, if you had, for example, a dupe, which I think is the second one here. So this is the duplicate. Then to do a 4-star of a duplicate, first you make a fresh C, and then I really should use a different font here so that there isn't a collision between the two. I'll maybe fix that up. So you make a fresh C, a fresh channel. You're going to sequence A, V, so that's this, and C. And then you're going to produce the dupe, but in place of A, in place of V, you're putting the C that you just did, and then the rest of the arguments. So let's go see if that rule holds here in our translation. So this is see if I can find the beginning. Didn't seem endless when I was writing it. Okay, so actually we can go through down to here, and you can see how it works. So the translation of when you have a prefix guarding a par is you make 2 new channels. You're going to duplicate whatever comes in on A onto C1 and C2. And then you're going to run the 4 on the 4-star on guarding P with C1 to X and Q with C2 to X. So this is really I mean, you can visualize it, right? So whatever X mentions are here are going to be passed along through C1 to P, and whatever X mentions are here in Q are going to be passed along through C2 to Q. That's the meaning of this translation. So let's see if we implement that. So here I make a couple of fresh names, and those are bound to C1 and C2. Then I do a translation of C1 as my subject, the same object, and L, which is the left-hand side of the par, and the translation of C2. So these always come with a subject, an object, and a continuation, right? That's the signature of this, because we know it's a 4 comprehension. So rather than pass the 4 comprehension along and unpack it, we just simply pass the subject, object, and continuation along. So that's the slight optimization. But these 2 expressions correspond precisely to this one and this one. And so what we're expecting is to get a par of those 2 together with a par of the duplicate and that par, and then a new on the front of that. So let's see if that's what happens. So we've now got the translation of the left and the translation of the right. And then, so we par those 2 together, that's right. Then we make a duplicate from the subject. Let's double check what the subject is. Yes, the subject is A, so that works. And so we have a dupe S C1 C2, which is just exactly the same as dupe A C1 C2. Oops. And then we wrap a new scope with the C1 and C2 around the exterior par. And so this code is exactly this equation. And likewise for the new. So what you do is this is kind of an interesting one, right? So if you have new of C prime of P guarded by the by a 4-star, then you make a fresh C and and then you put C for C prime and P, and then you do the 4-star translation. And what that does, you may think, well, this doesn't make any progress. Well, what it does is it guarantees that anything that might be bound will be moved out of the way, right? So in particular, anything that might, yeah, you see what I'm saying. So that'll move things out. So you actually will make progress. This won't loop forever. Yeah. So let's see if that's what happens. So there's a little bit of mishigash because she's only looking at singleton new, like her, but whereas I need to make sure that the new scope doesn't have multiple things in it. All right, so essentially she's got a recursion. If P has a new inside it, then you would do that recursion. So that's what I'm doing is so we'll loop through this and we translate the inner bit, right? So here's Q, we translate the Q and the rest of the names. And then when we form the process, we do the substitution of of this fresh one, C for in, which is the head of these of the name list, right? And then bind that with a new scope. So this is slightly inefficient in the sense that what I'll have is, if I have a new A, B, C, D, E, F, right? Then at the end of it, I'll get a new A prime, new B prime, new C prime, and so on. So you'll get this nested news as opposed to having them all bunched up. So this can be optimized, but I just wanted to make it as most like the equation as possible. Then if we go, so 0 should go to K. So here's the 0 expression, and it should go to K. Notice that it has to be a Y0 and not a pi 0. And the reason is because of this previous equation. We only ever hand the 4-star a translated continuation. So this will already be a Yoshida combinator 0 if it's a 0 at all, not a pi 0. So that's why in this case we're matching against a Y0, and then we produce the K of the subject. And if we look at the replication, so here's 4-star of a replication. So you guard the continuation with a message. It's essentially, here's a copy of P, and you forward along A to C, and you do the replication of that, right? So that's the trick. And then you so let's see if we do that. So here's our star P. We make a fresh C. We translate the par of P with the message, using C as our subject and O as our object. And assuming that successfully yields a Yoshida process, then we make a new expression with C as the bound variable, new bound variable, and we do a par of the forwarder from the subject to C and the translation. So it matches exactly this equation. So now we can move down to the dupe, and which is where I was headed, and take a look at that. So the way these are done is effectively, if you analyze her equations, she's first handling the cases of non-bound variables, and then she's handling the cases of bound variables. So this is when you have no binding. Obviously, there's no dupe mentioned here. And then if you look at the polarities, dupe is the only three variable one that has a positive polarity in the second position. So equation 10 would hold. So basically this holds and this holds and this holds in, let's see, and then this holds as well. So you have to apply equations 6, 10, and 11. So the way I analyzed this was to simply check to see if any of these are bound, right? So we check to see if any of these are the object, right? That's the bound variable in the 4-star, right? So if we, well, I won't go all the way back to the top. So basically, there are cases for all of the different bindings. So when nothing is bound, then equation 6 holds. When the second one is bound, regardless of whether the third one is bound or not, then equation 10 holds. When the third one is bound, then equation 11 holds. And when the first one is bound, I need to remind myself. When the first one is bound, equation 10 holds, I believe. Yeah. So we'll just check one, and you guys can go over the code at your leisure. So this one is equation 6, right? So we're expecting a sequence. We expect the dupe, and we're going to replace we're going to put the fresh variable in the third position on the sequence, and it's going to be in the first position of the dupe, and that's going to be a par. So let's just see if that is what's going on. So we've got a sequence and a dupe. That's good. The bound variable is in the third position of the sequence and in the first position of the dupe, and otherwise you have the two remaining variables. And this is in fact a new expression against the par expression. So this matches exactly with that code. So that gives you a sense of how to read the equations in either this paper or the OSHA Combinator paper and map them onto the code. That's basically a decoder ring, so to speak, for how to treat the equations as Scala code. Of course, you could also do it with Haskell or whatever. So that's so Rocom does that. So I changed the prompt to XCOM because it's basically cross combinator compilation. So that's but that's running now, and so my next step is to do the translation of the two different translation paths directly from Pi to row combinators and factored from Pi through the Yoshida combinators to row combinators. And I just need to find a spare hour or two to do that, and then that will be a completion of that piece of the puzzle, and people can play around with it and see how the translations work. I mean, one of the things that is most obvious is that, well, you can see it right here. Abstraction gives you enormous compression. This is basically the information. When you look, you've got 10 equations, or sorry, you've got 13 equations that are covering all of the different cases that abstraction is kind of boiling down into a single mechanism. And so that's really, really like when you translate abstracted things, then you get this big combinatorial explosion. And by the way, the same thing happens with SKI. SKI blows up. People tried to build practical compilers, right? So if the history of OCaml was attempting to do something, almost SKI-like, is categorical abstract machine, but essentially it's sort of a categorical combinator approach for the semantics, and that didn't pan out. It wasn't particularly efficient, and David Turner, who implemented a language called Miranda, took the SKI thing more seriously, but he realized there was a combinatorial explosion, and so he proposed these ideas of super combinators, so these mega combinators that did more of the abstraction work. And again, it really, the point is that abstraction is a very efficient mechanism for representing this aspect of computation, which is substitution, capture avoiding substitution. So when you compare this to the async pi, it's really striking, right? I mean, async pi is very, very short and sweet. I guess I don't have it nearby otherwise, but I think people can remember the async pi syntax. So that's one thing. And then it turns out that new is similarly compact, compressed. So when you unpack these things, you'll get explosions, combinatorial explosions in terms of the expressive power. However, the one thing that you do get on the other side is you get separation results. So when you don't have abstraction and you just have you just have the combinators, then you get these kind of separation results. So essentially she shows that there's you can get this idea of a basis for computation. So let's see, where is I'm just trying to find the results because they're expressed very nicely. There we go. So where is that little diagram? Come on. So essentially, she's able to find these subsystems of the pi calculus by considering different subsets of combinators and then compare their expressiveness, right? That's the trick. And she has it summarized, at least in one version of the paper, she has it summarized in a nice little cube diagram. There it is. Okay.
You mentioned this last time, right? When you remove something from, okay.
Yeah, so this is the diagram. So essentially what she's looking at is subsets of the different combinators, right? You don't get very far without message, so all the subsets are going to have message. And then, if you have duplicator, branch right, and branch left with message, then that's less expressive than if you have a sequence. And that's, you can see the different comparisons. And these correspond to that these correspond to different flavors of pi. So for example, there's affine and linear pi, there's a reflexive pi, and that's what these correspond to. So it's
and this is only by removing some part of calculus, right? Not just these are not about reducing what can be on some position.
So if you look here, D1 and D0 imposes additional disciplines, but by and large, it's mostly about subsets and combinators.
Okay.
Yeah. So anyway, so that's what you gain by, so you lose in terms of expressive power. So you have to write much more code in order to say the same kinds of things you can say with abstraction, with new binding. But you do get this kind of ability to compare expressiveness. So you can see the different the different calculi and how expressive they are, and that's kind of important. It gives you a crisp handle on the expressiveness of different subsets of the pi calculus. So that's why you pursue this. Now, if you think about it, right, one of the things that people haven't, like for example, Kairos in his paper where he introduces the behavioral spatial behavioral logic, he identifies this subset of pi calculus processes that for which the typing is decidable. Now, what would be interesting is to analyze that subset in terms of this diagram and see where it lives. And no one's done that. No one said, "Oh, I can take it on to find out exactly how expressive that is." Right. So that's this would be a way to figure out exactly how expressive that typable, that decidable set that Kairos finds, exactly how expressive it is. And we expect it to live somewhere on this diagram because there's no other places to live. So that's a really important line of research that nobody's taken on, but probably should be done.
And I'm not sure that I understand how in which units we can see this comparison of expressiveness.
It's relative, right? So this is the most expressive.
When
and these are incomparable, right? We can't compare them. But all three of these are less expressive than this one. So there are things you can say in here that you there are things you can say in here you can't say in here, and so on. Now these are incomparable in the sense that there's stuff you can say here that you can't say here. There's stuff you can say here that you can't say there. Right? And then this is strictly less expressive than this, and this is strictly less expressive than that. And so duplication is a big one, right? It's obviously the important one. And then same here. So this is less expressive than either of these. And then this is less expressive than that. So that's the way to read this diagram.
Okay. But this doesn't tell us exactly, when we have two branches, between branches, how to compare.
No, you can't. That's when there's branching, you can't compare them.
Okay.
Yeah. All right. So in other words, between this and this, there's stuff you can say here that you can't say here. And there's stuff you can say here that you can't say there.
Oh, so we can, I see.
Yeah.
We can see what is the common thing, but also if we have this connection, we cannot say anything about it.
That's right.
I see.
So so the reason I mentioned typing is because you could imagine that you identify type systems that pull out exactly these expressiveness classes. So you find a typing restriction on the spatial behavioral logic that picks out exactly this class, and one that picks out this class. Right. So no one's done that. No one's done this research. I actually predicted this in 2000 when this paper came out. One of the research programs that I looked at was coming up with type systems derived from the combinators themselves. And this was in advance of the Chi-race results. And when Chi-race results came out, I kept expecting someone to go and do that work. To pick out, these expressiveness classes relative via the type systems, because that's kind of the whole point of a type system, is that it classifies things. All right, I need to jump off, but
can I ask you just one short question? If when you say this is not expressive in another branch, you mean completely not expressive, not even with additional work with combinators that we already have in this branch?
So what I'm saying is, in the rightmost branch, there are processes you can form that you can't form in the middle branch. However, there are processes you can form in the middle branch that you can't form in the rightmost branch. And but by being in this part here means that the only expressions you're allowed to put together are message, duplicate, branch left, and branch right. And the only things you're allowed to do here, are the C1 together with message, duplicate, branch, right, and sequence.
Okay, not even with additional code to less optimized or.
The only thing you're allowed to use are the combinators, nothing else, just the combinators. We're only using combinators. That's kind of the whole point is. So
okay.
These combinators are sufficient to get you all of pi.
I see.
Yeah.
Okay. Yeah, thanks.
Yeah, sure. All right. Thank you, folks, for your time and attention. Hopefully this is useful for some folks.
Oh, yeah. Yeah, thanks.
Sure.
Yeah, thanks, Greg, for going over all that.
Pleasure. All right. We'll see some people on the stand-up in about 17 minutes.
See you.
Have a good day, everyone.
Bye.